Hello everyone. Today I'm going to talk about quantum computations in quantum gravity. This talk is based on these two articles. These are just the archive numbers for these articles, and we wrote the articles together with Grzegorz. And also you can find on GitHub, on the Quantum Cosmos GitHub, code for simulation presented in the second article. So first of all, let me give some motivation why we want to use quantum computers to do quantum gravity simulations. So quantum computers basically consist of qubits which are just two-level quantum systems. So Hilbert space describing a quantum computer has dimension which increases exponentially with a number of qubits. And in recent years, number of qubits in available quantum computers increases. For example, the largest one, IBM quantum computer Seattle, has 433 qubits. And here you can see layout of these qubits, connections between them. And in general, quantum computers are exponentially hard to simulate on classical computers. Of course, there are some classes of quantum states that are that can be efficiently simulated, but in general, arbitrary state is exponentially hard to simulate. And we know that there are some quantum algorithms that are exponentially faster than classical ones. For example, the best known example is Shor's algorithm, which factorizes integers and which is faster than all known classical algorithms. But there are also some problems with quantum computers. First of all, current quantum computers are noisy, so each gate applied to quantum register and each measurement at the end introduce some errors. The second problem is that current qubits has short decoherence time, so we can apply only a small number of gates before qubit decoheres and becomes completely random. There are, of course, solutions to these problems. You can use, for example, error correction codes. But error correction codes require that each logical qubit need to be encoded using many physical qubits, and similarly, each logical gate need to be encoded using many physical gates. So, to run some quantum algorithm, we need a lot qubits, many more than it is in ideal case in theoretical algorithm. So currently this is not possible to run such algorithms with error correction codes on some large scale. Maybe in the future, and then we will have fault-tolerant quantum computers. But now we are in noisy intermediate scale quantum era. And we can run short circuits, and also we can run quite good variational algorithms because, for example, when we look for minimum of some function, then some quantum noise is assuming enough deep minimum. Then quantum noise is not very big problem because we can still find this minimum function. Or even quantum noise can be helpful because quantum noise can take away from some shallow local minima during looking for this global minimum. And there is also another problem, namely transition between quantum and classical data, because usually we need to first encode some classical data into quantum register, then perform some quantum algorithm, and then at the end extract classical data again from this quantum register. But often the case is that encoding quantum data is exponentially hard, so we need exponentially many gates to encode some classical data, and also decoding classical data sometimes, often, requires exponentially many measurements at the end. So this is the problem, because, okay, our, let's say, quantum algorithm is exponentially fast, but encoding and decoding is exponentially slow, so there is no sense to do it. So the solution, partial solution, is to work as long as possible only on quantum data. And all of these problems and solutions to these problems lead us to the conclusion that one of the possible application of quantum computers in near future, not in the far future, are simulations of quantum systems in physics. In our case, these are simulations of quantum gravity systems, and in this talk I will focus on loop quantum gravity, which is a background-independent, not perturbative approach to quantum gravity. Short review of loop quantum gravity. This is canonical quantization of gravity. So we have Einstein-Hilbert action, then we switch to Hamiltonian formalism, and we obtain gravity as a fully constrained quantum system, not quantum yet, but fully constrained system. Then introducing Ashtekar variables, we can formulate gravity as a SU2 H theory and then quantize it. And in quantum gravity, quantum geometry of space is represented by spin networks, which are graphs with links labeled by SU2 holonomies and SU2 invariant nodes. And in this picture, nodes of these spin networks can be associated with a quanta of volume and links with areas around these volumes. And taking a set of all spin networks for all possible graphs up to the theoremorphisms and all possible holonomies, we obtain kinematical Hilbert space of loop quantum gravity. And also it is worth to mention here that these methods presented here can be used not only for spin networks but also for general gauge theories with completely proven connection form. So this can be applied also beyond quantum gravity systems. And in our case, we focus on 4-valent spin networks. In this case, each node is dual to tetrahedron, and also we focus on spin networks where holonomies on links are in SU2 fundamental representation. In other words, links are labeled by spins 1/2, and this case is quite convenient to encode on quantum computer because when 4 spins 1/2 meet at the node of spin network, then after applying Gauss constraint or SU2 invariance, we obtain a 2-dimensional subspace. In other words, SU2 invariant subspace of 4 spins 1/2 is 2-dimensional, so can be encoded on qubit. So this is very convenient case because links are spins 1/2, so qubits, and also intertwined state of the node after imposing Gauss constraint is also a qubit. So we want to generate state of this spin networks on quantum register. So let's take a look on some fragment of some spin network. So we have 2 nodes connected by some link with holonomies H, holonomy H, E, and this fragment of spin network corresponds to expression which is obtained by taking Wigner 4J symbol corresponding to node and Wigner matrix corresponding to this SU2 holonomy, and then we make a contraction of the magnetic indices of these tensors. And we want to perform something like that on quantum computer. So first of all, we need to have some rings, and ring can be represented here as a pair of qubits, and moreover, from unitarity of holonomy, unitarity of holonomy induces that this pair of qubits will be maximally entangled. So we need to prepare maximally entangled pair of qubits. For example, let's say we have some holonomy equal identity, then we need to prepare this state 0, 1, minus 1, 0 on quantum computer, and we can do it applying some NOT gates, Hadamard gate, control NOT gate, and so on. So we have links, and then we need to have something corresponding to nodes, and we can construct this W circuit, which acting on state K000 gives a superposition of states with Wigner voltage symbols as coefficients. And we have some explicit construction of this W operator, consists of some gates, square root of swap, S gate, T gate, and so on. And now, having these rings and nodes, we can see on some very simple explicit example how we can construct spin network. So we have two nodes connected by 4 links with holonomies H1, 2, 3, 4. So we need to prepare 4 pairs of qubits corresponding to these links, and then we need to apply Gauss constraint. So we need to apply kind of projection, and this projection can be prepared by taking W dagger, this W from the previous slide, W dagger, and projection on 3 qubits 0, 0, 0 here, and applying this at the end we obtain on these 2 qubits, first one and fifth one, we obtain state corresponding to state of this very simple spin network type. Okay, and then we have this state on these 2 qubits, and we can do whatever we want with it. For example, we can do it quantum tomography to obtain explicit form of the state, but this is not the best idea because quantum tomography is requires exponentially many measurements, so this is not the best idea. The better idea is to apply there some parameterized ansatz, and then tune these parameters such that this ansatz will reproduce this state. So we have here, we have on these 2 qubits this state of spin network, and then we tune these parameters to obtain basically 0, 0 here. So to obtain U such that U dagger generates this 2 qubit state. So we can define some cost function and perform a variational algorithm to find optimal parameters theta. And this is hybrid algorithm. Quantum computer is used only to compute cost function or gradient of cost function, and classical optimizer is used to minimize this cost function. Okay, and exactly in the same way, we can generalize this method to arbitrary spin network. we can have some pentagram spin network. We prepare 10 pairs of qubits, we apply 5 projections, and then we transfer this result on some 5-qubit parameterized answers. And in this method, number of qubits required is equal 4 times number of nodes of spin network. And also, to compute this cost function, we need quite a lot of measurements. So, to construct larger spin networks, it is better to first build some building blocks and then glue them together to obtain higher number of nodes. For example, we can prepare kind of open pentagram, let's say. So we prepare 10 links, but then we apply only 4 projections, and at the end we have 4 nodes and 4 free links. And then using this as a building block, we can, for example, glue such 2 open pentagrams and obtain some spin network with 10 nodes. Okay, so it was first method, and now we are developing improved method, which is similar but is more tensor network inspired. So we prepare quantum circuits for different positions of indices in Wigner 4J symbol. So we have 4 magnetic indices, which can be lower, upper, and so on. And we prepare different circuits for different positions of indices, and we have explicit form of this circuits. Here I just put some squares, and also holonomy, which is represented by Wigner matrix. Here is expressed on a single qubit as a single gate acting on this qubit, not as a pair of qubits, and it is connected with known in quantum information theory, so-called Choi-Miałkowski isomorphism, that quantum state is kind of dual to a quantum channel. So here we say that you have quantum channel which is dual to the previous one, quantum state of pair of qubits. And using this method we can construct quantum circuit for spin network using lower number of qubits. For example, we have pentagram spin network, we translate this to tensor network, so we have tensors corresponding to Wigner symbols, tensors corresponding to holonomies, and they are contracted together, and then we can translate this tensor network to quantum circuit. And at the end we obtain state of this pentagram in this case. So we have explicit procedure to translate arbitrary spin network into some quantum network. In this case also we can prepare kind of open spin network. This is a bit different open than before, because now we have still 5 nodes, but we broke, let's say, this one link. And this kind of open spin networks are interesting not only as building blocks for larger networks, but also because this kind of spin network represents some volume. Yes, we have some volumes, and this volumes is enclosed in some area. So this kind of spin networks can be used to look at some kind of holographic-like properties of states represented by spin networks. And our methods presented here, of course, can be viewed as just a tool alternative to classical numerical computations, but also it can be viewed as a tool to translate quantum geometry states onto quantum circuit, and thanks to this we can apply some quantum information, quantum computation tools to analyze this quantum geometry of space. For example, you can construct a bulk-Bandari map. Bulk-Bandari map is a map from degrees of freedom in some volume to degrees of freedom on surface around this volume. And we can, using our method, we can explicitly construct a quantum circuit which takes degrees of freedom in volume and gives degrees of freedom at the boundary, and we can construct this using elementary gates. So then we can apply some quantum information tools to analyze it. For example, we can take a look on complexity, as Mario said in the previous talk. Complexity, for example, can be defined as a number of gates required to obtain some state. So here we can explicitly give this number of gates. So of course this is not necessarily minimal number of gates, so this is rather some bound for complexity, but yes, but it is kind of measure of complexity. Or we can look at the quantum information structure of this circuit on some entanglement structure between different degrees of freedom and so on. So basically you can translate this quantum geometry problems to quantum information problems. Okay, so to sum up, three takeaway messages: that we can explicitly construct a quantum circuit for arbitrary spin networks, arbitrary for valent which spins 1/2, and this can be viewed as just a tool, an alternative to classical one, or as a tool to quantum information characterization of quantum gravity states. Thank you.
So we have time for questions. Rick.
So I know a little about quantum gravity states, but I have no idea what we are doing and how possibly it can be useful directly applied in quantum. But in particular, I mean, so what I can ask are some subtleties which are maybe measured zero. In full picture, but something which I just noticed and explicitly didn't understand. So for instance, in one of your slides you said that let us set holonomy to be 1.
Yeah.
Okay, so holonomy is a function of connection. So this is like considering a wave function and saying let us consider the value of wave function at this specific point in space. Okay, one can do it, but it doesn't make much sense. Usually, wave function doesn't have much sense at a given point. It has sense when it is integrated. And so I don't know what is the physical meaning of setting this.
Okay, here we consider this state for concrete holonomies on each link. But in principle, we can take some superposition of polynomials. When we take polynomial as a unitary operator, then we can construct maximally entangled pair of qubits, but we can also take some superposition of polynomials on this link, and it is also translated to some pair of qubits, but not maximally entangled. So this is just example, probably not physically meaning, but just simple example.
And what if you didn't evaluate age on a flat connection, but if you just considered arbitrary?
Okay, so if I put here arbitrary connection, then I just need to modify this circuit, and it is very easy, let's say. So I can give you explicit form of this circuit for arbitrary polynomial.
Okay, and the second is similar detail also. Some others, like you consider those several possibilities for formal and intertwiner, and in particular you distinguish between intertwiner that has only upper indices or only lower indices, or first to upper and second to lower. So actually, this is all those intertwiners, they define the same state. So the same state can be, depending on how you orient edges, may be represented either by any of those intertwiners. So I would say this is, from the point of view of state, from the point of view, we are still considering the same
yes,
state.
This is more technical.
This is written in a letter.
Yes, this is more technical, but it is more efficient in number of qubits to use different qubits for different circuits for different positions of indices. But of course, at the end, yeah, this doesn't matter. Also, for example, because we can lower and upper these indices by this isomorphism, we can also construct, for example, quantum circuit corresponding to this G mu prime, mm prime, and then, for example, we can use only, let's say, this circuit, and then we can apply this G prime to contract this with something that requires lower index. But this is just technical thing that this different operators for different position of indices is more efficient, let's say. But of course, this is just different position of indices.
Okay.
Any more questions? No, yes. Thank you.